accepting to give this seminar. So today we have Minmin Wang from Sussex University, who will talk about geometry of large random intersection graph inside a critical window. Minmin.
And thanks, Pablo. And so I'm very glad to be here. And so I want to talk about this random intersection graph. And so the motivation for that is actually quite simple. So many random graphs we're familiar with, so they have independent edge probability, so which means the edges are sampled independently. Okay, so which makes them nicer to study and have brought us many beautiful results. But then at some point, people start asking, well, what can you do with random graphs with dependent edge probabilities? Okay, so one situation that such a question can arise is if you want to have some sort of a community structure inside your graph. Okay, so in terms of graphs, this simply means that you have a subset of vertices which are more likely to connect with each other than with someone else outside the group. Okay, so there are various ways to achieve this community structure. So for example, you can consider a random geometric graph, which is not the same I'm going to consider here. So here I'm just introducing a very, in a sense, a very simple random graph model without, embedding it into a Euclidean space. So this is called the random intersection graph. Okay, and to be such a graph, we first need a bipartite graph. Okay, so a bipartite graph is basically just a graph with two sets of vertices. So in this context, it's very natural to call one set of vertices as individuals and the other set of vertices as the groups that the individuals can potentially join. Okay. So the edges in this bipartite graph is always between an individual and a group. So never between two individuals, not between groups. Okay. Right, so you might say these n individuals and n groups. I'm going to run a random graph by letting each individual to join a group independently with probability B. Okay. So here on the right-hand side, I have an example of such a bipartite graph. Okay, so the black vertices are the individuals, so there are n of them, and then the white vertices are the groups. So you have in total m of them. Okay, and in this example, you have in total 6 edges. Okay, in this graph. I'm going to call this random bipartite graph B N and B. Right. Okay, so given such a graph, now I'm going to build my random intersection graph, okay, as a function of the bipartite graph. Okay, the random intersection graph only has n vertices. Okay, so they represent the n individuals. Okay, in the previous construction. And I'm going to join two individuals with an edge if and only if. So these two individuals, they have joined the same group in the previous construction. Okay. So again, back to this example. So this is the random intersection graph corresponding to the bipartite graph above. Okay. So for example, if you look at the group number 2, it contains 4 individuals, 1, 2, 3, 4. And according to this definition, these 4 individuals, they're all connected with each other with an edge. Okay, so this creates a copy of the complete graph K4 inside this random intersection graph. Okay, so this example shows that actually each group will induce a copy of the complete graph inside the random intersection graph. Okay, so this is also in a graph theory called a clique. Okay, a copy of a small complete graph. Okay. Right, so this is the model I'm interested in, okay? And hopefully from this very simple example, you can already see that the random intersection graph, unlike for example, the classic L-running graph, is not locally tree-like. So you have these structures of cliques, okay, representing the community structure. But at the same time, it is just a projection of this bipartite graph, which is much nicer, which is indeed locally tree-like. Okay, so you have this graph has this interesting feature, but it's also quite accessible. Right. So in this talk, I'm going to be interested in the asymptotic regime where both the number of individuals and the number of groups go to infinity. Okay, so these two parameters, m and n, go to infinity. So may go to infinity with different speeds. I'll come back to that later on. And also assume P. So this is the probability of having an edge in the bipartite graph. So assume this goes to 0. Okay. So here are some properties of the random intersection graph we can deduce quite easily. So the first, let's look at the probability of having an edge in the random intersection graph. Okay. So everybody's displayed the same row here. So I can just pick any two. So let's say I and J. This is the probability that I is adjacent to J in the random intersection graph. Okay. Which I denote as G, N, and P. Okay. So what is this probability? Well, according to my definition, the probability of the complementary so according to the definition, this happens if and only if I can find a group that contains both individuals, right? So the probability of the complementary of this event is given by 1 minus p squared. So this is the probability of not having both individuals in one group, and then raised to the power m. Okay. So in the asymptotic regime, I consider this probability is roughly of the order np squared. Right. So that is the probability of having an edge. And then you multiply by the number of vertices available. So that gives you the expected degree of a vertex. So that is np squared. Okay. So I'm going to consider the case where the expected vertex degree is going to converge, let's say, to some constant c. Okay. So this is the so-called sparse regime in random graph. Okay. So with this constraint, we can easily work out what p I need to take. So p should be of the form square root c over mn. Okay. So I'm going to fix this type of p from now on. Right, now I can increase the value of c, this constant c, okay? And then try to understand the behavior of the graph, okay? So one thing which is often studied in random graph is the size of the largest kinetic component, okay? So if you want to study that, it turns out you can use a branching process approximation, very much like the branching process approximation in the L-running graph case. Okay. So, and the outcome of that analysis is just the size of the largest kinetic component in the random intersection graph undergoes a phase transition at exactly the same point as the branching process. Okay, so the branching process is critical when the expected degree of a vertex is exactly 1, so the phase transition happens at c equal to 1. Okay, so this is the case I'm going to take from now on. So I'm going to interest in the critical case, that is the probability p is going to take this form 1 over square root mn. Okay. So in fact, we could be a little bit more relaxed about that. So we can put a small arrow term. Okay, we're going to see what the order of this arrow term later on. And that's not going to change the big picture of the graph. Okay, So this is actually called the critical window. Right, so I'm interested in the random intersection graph when P is of this form. Okay. So up to this point, so these arguments follow very much the footprint of the eldest running graph. But now let's see something a little bit different. Okay. So now I need to consider the relative speed between m and n going to infinity. So just to simplify things a bit, I'm going to assume that m is this power function of n. Okay, so it's not a very important assumption, but it simplifies a little bit the presentation. Here I'm interested in a quantity called the clustering coefficient. Okay, so what is the clustering coefficient? So for that, I just take 3 vertices, let's say 1, 2, 3. Okay, so assuming that both 2 and 3 are already connected to the vertex 1, so what is the probability of 2 and 3 connected to each other? Okay, so this conditional probability is called the clustering coefficient of this graph. In the case of the random intersection graph, this probability can be computed rather easily, right? So let's just see the case of the triangle, so the nominator here. Okay, so to have such a triangle, you can have 2 possibilities. Either all 3 of them also belong to the same group. Okay, so that happens with probability p cubed for one group, so times m, that gives you the first possibility. Or you can have each of these edges coming from a different group. Okay, so in that case, these edges are roughly independent. And we already know the probability of having an edge in the random intersection graph is PE. So the second possibility is given by PE cubed. Okay, and then you can do the denominator in a similar way. So the asymptotic behavior of this ratio, okay, is basically determined by the balance of these 2 terms on the denominator. Okay, so if the second term p squared dominate, okay, so in terms of the relation between m and n, that turns out to be the case where alpha is exactly larger than 1. Okay, so m goes to infinity much quicker than n. So if that is the case, you can check very easily that the clustering coefficient goes to 0. Indeed, so I'm going to call this regime the lightly clustered regime. Okay, and in the opposite, okay, so which is alpha less than 1, then the term mp squared will dominate, and then the clustering coefficient will tend to 1. Okay, and between these 2 cases, okay.
Hey, ask a question.
Sure, of course.
Yeah, so just to check whether I'm seeing things in the right way. So yeah. The larger the alpha is, the more your graph looks like the classical Erdos range, right?
Yeah, exactly. But this is something I'll talk about later. Yeah, but that is the main message. You're getting ahead of me. Thanks.
Thank you.
Right. I mean, okay. So right. So finally, just finishing this slide. So if alpha is 1, then this clustering coefficient will depend on the exact ratio between m and n. So this is given by this parameter theta, and then so it gives you this function of theta. So it's a function between, it takes value between 0 and 1. So if theta goes to 0, it tends to 1, and then if theta goes to infinity, it tends to 0. Okay, so basically it means you can, so this is a case which interpolate between the lightly clustered and the heavily clustered region. Okay, so this is already pointed out. So what we see from this analysis on the clustering coefficient is it looks like as alpha decreases, okay, your random intersection graph is becoming less and less similar to the eldest running graph. Okay, and in a way, the result of this talk will confirm this feeling. All right. Okay. So yes, and for just one thing I forgot to mention, because for this conclusion to make sense, if you look at the classic eldest running GNP, then the clustering coefficient tends to 0 in the sparse regime. All right. Okay. So that's the reason I'm saying it's becoming less and less similar when alpha decreases. All right. So here, my main question is, what do the large components of this random intersection graph look like? Okay. So there are various ways to extract geometry from the random graph, and the approach I'm taking is the so-called scaling limiter graph. Okay, what I mean by this is, so you take a kinetic graph. So in this case, the natural candidate is just the case largest kinetic component in your random intersection graph. So I'm going to give it a name, so call it C and MK, right? We're going to consider this kinetic graph as a metric space, okay? The metric is just the graph distance, okay? So as the size of your graph goes to infinity, the diameter of your component is going to infinity, okay? So to keep things compact, you have to rescale the graph distance, okay? So the aim here is to find appropriate sequence real numbers alpha and m, put it in front of the graph distance, and then you look at this rescaled metric space CK and MM. Hopefully you will find a limit object so that this random metric space will converge to this limit object. So here I'm talking about convergence of metric space. There's a natural notion of topology for that. It's called Gromov-Hausdorff topology. And I'm not going to introduce that topology because we don't exactly need that definition for the rest of the talk. Just one thing I'm going to mention here is once you have the convergence in the Gromov-Hausdorff topology, a thing you get automatically is the convergence of the diameter. Okay, so this means that the diameter of your discrete graph or your discrete kinetic components rescaled by this factor Nm should converge to the diameter of the limit object, and that is going to be finite almost surely because you want something compact. Okay, and from there you immediately realize that this normalizing constant should be taken as the order of the inverse of the diameter. Okay, so that is usually the way how we find out this. We find this normalizing sequence. Okay, so this is the aim. So sort of the prototype result of the scaling limit of random graph is done for the eldest running graph inside the critical window. And this is discovered by Berry, Bruton, Goldschmidt in 2012, based on also some previous results of eldest. I'm going to say a bit more on the result, okay, because this is going to work as a kind of a benchmark case, okay? We're going to make comparison basically between the eldest running graph and the random intersection graph, okay? So before doing that, we need to think a little bit carefully about the parameter of the L-running graph. Okay, so if you think a little bit about that, so you will realize the correct parameter to plug in here for the L-running graph is not P, but PE. So that is the probability of having an edge in the random intersection graph. Okay, so the game is basically compare G and PE versus the corresponding random intersection graph. Okay, so before doing that, let me first tell you, so what happens in the L-running graph. Okay, so in that case, the result of the variable Schmidt tells us, so the correct critical window to take is given by this form. So 1/n is a critical point, and then you have a width of the critical window of the order n to the power -1/3. Okay, and then this lambda just parameterize your critical window. So lambda is any real number between -infinity and +infinity. So in that case, you take the case largest kinetic component of your L-running graph, so I denote as C and K. You rescale the graph distance by this factor n to the power -1/3, and turns out it will converge in distribution to some limit object. Actually, the whole sequence of kinetic components will converge, right? And this limit object also has a very explicit construction. So for that, you first need to take the parabolic function. Okay, so 2 lambda t minus 1/2 t squared, and then you run a Brownian motion on top of that. Okay, so that gives you this process st. Okay, so you look at the excursion of this st above its running infimum. As it turns out, even if there are infinite many of such excursions, you can still rank them in decreasing order of their lengths. Okay, so you take the case longest excursion. Okay, let's say this one. So this is your case longest excursion, and somehow you should think of this excursion as a contour of your graph. Okay, so from there you can extract directly the distance, this distance d of the limit object. Okay, we're going to see a little bit more later on. Okay, anyway, so this is the result concerning the scaling limit for the L-running graph. Okay, all right, and this is a simulation of a large kinetic component of the L-running graph inside the critical window. Right. So just to give you an overview of the result. So in a nutshell, we're going to see that the scaling limit of the random intersection graph is going to depend on which cluster regime you're in. Okay. If you are in the lightly cluster regime, okay, so that is a case which is similar to the L-running graph. Okay, it turns out you have exactly the same order for the diameter, so it's n to the power 1/3, and you have exactly the same limit object as the L-running. Okay, if you go to moderate cluster, the order of the diameter is still the same, n to the power 1/3, but the limit object is different. Okay, it's not. It still has a relation with the L-running, but it's certainly something different. And finally, if you go to the heavily clustered, then the order of the diameter changes. It changes to n to the 1/3, that is much smaller than n to the 1/3. Okay, but you have the same limit object. The reason for that is because in that case, what you have is all these little clicks and around the vertices, but all these clicks, they just have diameter 1. So when you go to the scaling limit, they're all crushed. Okay, so that's the reason why you get the same limit object. Okay. Right, so I'm going to come back with a bit more precise statement on this scaling limit. But just to have some perspective, for comparison, let's look at a convergence, but now in a much stronger topology. Okay, so just to remind myself, if we have two probability matches, let's say mu and nu, on the same matrix space, the total variation distance between mu and mu is the maximal differences in terms of the masses of the sets over all the sets B. Okay. Equivalently, you can see this from the coupling. Okay, so here the coupling is a pair of random variables x and y. Okay, so the marginals of x is mu, and the marginal of y is given by mu. Okay, now you look at the probabilities that x is different from y, and you minimize this probability among all the coupling possible, and that gives you again another definition of the total variation distance. Okay, so here let's take mu n to be the law of the random intersection graph, and mu n to be the law of the corresponding L-dot random graph. Okay, so it turns out if n goes to infinity, and you're in the region where alpha is strictly greater than 3, then this true distribution is going to be identical in the total variation distance. Okay, and if alpha is less than 3, then they're going to be asymptotically singular with respect to each other. Okay, so this is a result proved by Brandon Bretzler and Nagaraj rather recently. So I should mention that their result is quite strong because it actually works for any sequence of P inside the interval 0, 1. Okay, so if you just look at the sparse region, it's not that difficult to prove, and the difficulty is to extend that to the whole interval. But anyway, if we try to compare this result with the previous one on the scaling limit, okay, so we could kind of interpret it in an intuitive way like that. So if you put a random intersection graph with an L-dot running graph side by side, okay, so if you stand from afar, okay, stand some distance away, so you have the view of the whole landscape, then in that case, you only need alpha greater than 1 for you to say these two looks the same to you. But if now you really stand next to the pictures, okay, you want to compare detail by detail, then you need alpha greater than 3 to say they are identical. Okay, the kind of the intuition here. Right. Okay, so now I'm going back to the scaling limit result. So here now I'm going to tell you a bit more how we get this kind of result via a graph exploration. Okay, but if we just go back to this overview of the result, okay, so it looks like we have 3 cases to consider, but actually we only need to focus our mind on one simple regime. The reason is that, so if you look back at the bipartite graph, there's a symmetry between M and N. Okay, so if you think of that, and then you just exchange the row of M and N there, okay, then you will realize that the heavily clustered regime will bring you back to a largely clustered regime after you exchange the row of M and N. Okay, so we can always reduce discussion in the third case to the first one. Okay, now let's look at the moderated cluster regime. Okay, so here you have a parameter theta, which is the ratio between M and N. Okay, So at least formally, if you let this ratio go to infinity, then you should recover the lightly cluster regime. Okay. So what I'm saying here is actually we only need to concentrate on the moderate cluster regime, and we can kind of recover the two other cases by taking the limit, by taking theta to different limit. Okay, so this is what I'm going to do. From now on, I'm just going to consider this moderately cluster regime. Right, as I said before, so to get to scaling limit, we use a sorted graph exploration. It's a DAPS first good exploration. And we do it first on the bipartite graph, okay, which will then induce an exploration on the random intersection graph. Okay. So again, if you're familiar with the technique on the L-dish running graph, this will appear a very natural extension to you. Okay. So if not, don't worry, the idea is very simple. So this exploration graph is just going to help us to discover the graph, but one individual step. Okay. And to kind of keep track of how much of the graph we have discovered, we're going to label individuals as we progress. Okay. So the individuals are going to be labeled unseen. So these are the unexplored ones. Or things, they are the explored ones. There's a third list category called active. So the active individuals are going to tell what we're going to explore in the next step. So that determines the order of the exploration. Okay, so that's the side of the individuals. On the side of groups, it's things are simpler. So a group is either unseen or seen. All right, so to start this exploration, so we first declare every individual in the group as unseen. Okay, and then we need to start somewhere. So let's just pick the individual one. Okay, so immediately we're going to declare it as seen. Right. What we're going to do here is to explore the neighborhood of this individual. Okay, so all its neighbors are on the side of groups. Okay. So here in this example, the individual one belongs to two groups, 1 and 2. So this will form the set M1. So M1 is the set of all the unseen neighbors of the individual one, because we are very at the starting point of this exploration. So every neighbor is unseen, but things will change later on. And once we've done that, we're going to declare everyone in this set M1 as seen. Okay. Right. So this is the first neighborhood, and then we go back to the side of the individuals. Okay. So we're going to look at all the unseen neighbors of the members of M1. So these are the neighbors of the individual. Okay, and they are all individuals. So in this example, you have 2, 3, 4, 3 vertices. And once you have discovered this set, which I call N1, okay, call the N1, we're going to declare each element of this in this neighborhood as active. Okay, so the active vertices actually they form a queue, so you have an order on them. And what you do is every time you add new members to this queue, you put them at the top of the queue. Okay, so here we have these 3 members. You put a random order among these 3, it doesn't really matter, but then you put to the top of the queue. Okay, and now you have basically finished the exploration of the individual one. Okay, and the next step is pick an active individual. Okay, so in this case, you can pick 2 and look at similar things. You can look at the neighbor of 2, and then you look at the neighbors of the neighbors 2, and so on and so forth. Okay, so if you don't have any active individual, then we just pick a uniform individual among all the individuals that have not been explored so far. And if you don't have any such individuals, it means you have explored every individual. So in that case, you may still have some groups left, but they are all isolated. Okay, so that is the time to stop your graph exploration. Okay, so that's the algorithm for the DAPS first exploration. Entering this exploration, we immediately have a pair of random walks. Okay, so I call them DAPS first walk. So it's a two-dimension discrete time stochastic process, RKSK. So they both start from 0. Okay, and the increment of RK at time k is given by the size of the neighbors of the individuals that individually explored at step k, okay, on the group side. Okay, so these are groups. Okay, and you try to make things center a bit. So you subtract this drift minus square root sigma. Sorry, theta. And the other ingredient, so the other coding process, SK, so it has the increment given by the size of the neighborhood, but on the individual side, okay? And then you subtract a drifted one, okay? So this is the pair of the DAPS first walk, okay? So some nice properties of this DAPS first work. So first thing we realize is each time your SK hits a new minimum point, it means that you're going to a new component of the graph. Okay, so by just keeping track of the infimum of your SK, you know how many components you have explored. And if you look a little bit closer to the previous exploration, so actually you never explore a vertex as been seen before, which means that the exploration actually produces a spanning tree of the connected component of the graph. And if you put all the components together, then you get a spanning forest of the graph. Okay, so once you have a forest, it's very natural to define a height, the so-called height process. Okay, that is just the height of the individual which is explored at step k in this spanning forest. Okay, so I'll call this quantity HK, and it turns out HK can be expressed as a function of the Sj, so j up to k. Okay, so all these steps up to k. It's an explicit and not very difficult function, but problem is this is not a continuous function in any usual topology. Okay, and that would be a problem later on. Okay, so once you have the height process, basically that gives you the graph distance of the spanning forest. Okay, and to go to the graph, what is missing is just some extra edges. So these are called surplus edges. Okay, so if you have a surplus edges, that means there is a cycle in your graph. Okay, but one good thing about these surplus edges is actually as long as you stay inside the critical window, so you're not far from the critical case, this number of surplus edges are going to remain bounded. Okay, per in each kinetic component. Okay, and you can actually show that this number has a Poisson distribution, and you can work out where these surplus edges are situated. It's not a very difficult thing. So the message here is you don't need to worry too much about surplus edges, and to prove the convergence of graph. Okay, so the main point, the main job is to prove the convergence of the height process for the spanning forest. Okay, so that is usually the strategy. And from there, you can automatically deduce the convergence of graph in the Gromov-Hausdorff topology. Okay, and then so here is the main result concerning the scaling limit of this coding process. Okay, so as I said, we're in the moderately clustered regime. So m over n is given by this ratio theta. So it turns out that the critical window has the same comparable size as the Elder-Schrödinger case. Okay, so again, it has this term n to the power -1/3. Okay, so in that case, we look at this tripletive stochastic process that encode the graph. Okay, Rs and the hypers H. Okay, so you rescale time by this factor n to the power 2/3 and space by this power n to the power 1/3. Okay, and then you get a limit, a triplet of a linear process. Okay, R, S, and H. So what are these limit process? Let's start with R and S. Okay, so for that you need two independent Brownian motions. So R is basically a multivariate Brownian motion plus some drift, linear drift, and a parabolic drift. Okay, S is similarly defined. Okay, and then from S you can define the limit height process. Okay, so the limit height process is actually a very simple function of the process S. So it's just a multiple times the process S reflected above its running increment. So this only works in the limit case. In the discrete case, we don't have this relationship. So something magical happens while doing the limit. Okay, so just to double check, as I said, if we send the theta to infinity, we should recover the lightly clustered regime, and that cluster regime should have the same limit as the Elder-Schrödinger graph. So you can check this is indeed the case. Okay. Right, so probably have a little bit time to very quickly talk about the proof. So how do we get this limit theorem for the coding process? If we just want to look at the first two components, R and S, this is not very hard because it is a semi-martingale. So we have standard tools for convergence of this process. Okay. The problem is with the high process HK. Okay. So as I mentioned before, H itself is a function of S, but it's not a continuous function. And so the convergence of S does not automatically imply the convergence of the high process. And if you look at the distributional properties of this high process, it's also quite bad. It's not a Markovian in general, and it's also not a semi-martingale. So we don't have user tools, we don't have tools for convergence of the process like that. Okay. So what helps us here is, well, things are a bit difficult because we don't have RID increments. Okay, so you look at this RK and SK, they don't have exactly independent and the same increments. Okay, so let's change things a bit. So let's consider a simple case where you do have an IID increment. So you just take the first increment and you just replicate that increment for all the other time steps. Okay, so call this the corresponding process, the tilde process. Okay, in that case, okay, you can show, say, the limit process would just be some sort of Brownian motions. Okay, without the parabolic drift. Okay, and turns out, so there's a result of together and the gas, which says this convergence also extends to the height process. Okay, so in the IID case, we can do the proof. Okay, now what we need is just to relate to the IID case. Okay, so this is helped by the Jigsaw theorem, right? So if you look at the limit process, okay, RS and SS, so comparing to the tilde process, where you lose is just a parabolic drift. Okay, so according to Jigsaw theorem, you have an absolute continuity relationship between these two. And then H is a function of the S, So this relation extends to the height process as well. Okay. Now this is what happens in the limit. So you want something similar but discrete. So you go back to the discrete process and find out there is a similar relationship indeed. So the proof just consists in proving the convergence of the random-Nikodym derivatives. Okay. And then kind of the final twist of the proof is where we don't prove the convergence of this discrete random-Nikodym derivative directly because it is actually quite complicated. So in the first step, we use a Poisson approximation to approximate this discrete coding process. Okay, so the RKSK, they have binomial, kind of a mixed binomial increment, which makes things a little bit messy. So you use a Poisson increment to approximate that, and things become a little bit smoother. Okay, so that, I think that's the main idea of the proof. Okay, so I think I'm going to stop here. Thank you very much for your attention.
Thank you very much, Minmin, for this nice talk.
Thanks.
Is there any question or comment? So I have a question about this rescaling with n to the 2/3 and 1/3.
Yes.
Is this obvious that you have to take this scaling, or how will you justify it?
Right, I mean, okay, so no, it's not exactly obvious, but okay, so it's helped by two things. So first, you have a Brownian limit, so you know you're kind of in the standard regime of Brownian scaling. So that kind of explain the relation 1/3 and 2/3, right? And then yes, so from a purely combinatory point of view, so 2/3 because the largest kinetic component in the graph is disorder. Yeah, and then 1/3, yeah, that is something you need to work a little bit, but basically that tells you the order of the diameter of the graph. So yeah, that's the combinatory interpretation.
Okay, no, well, it's okay. It's a good answer.
Yeah.
Thank you. The other thing is about this K is the component size, right? The component label,
that's
right?
the order, yeah, like 1 is the largest, 2 is the second largest, and third largest.
But here you make it work as time in some sense.
No, so here you don't really say from the coding process, you don't see it because to extract the component, you have to look at the excursions. Okay,
Yeah.
so if this is the S, then you look at one excursion corresponding to one component. Okay, and then they are not exactly in the order you want. So you need to have all the components and rank them, and yeah, but yeah, it's a little bit more complicated that. But then the nice thing is once you have the convergence of the S, then automatically that gives you a convergence of all the components. Because everything is contained there.
So in some sense, the time for you is the exploration. This exploration.
Yes. So the time for in the coding process is exactly the step in the exploration.
Okay.
Yeah. That is a little bit artificial. Yeah.
Okay. Thank you. Is there any other question or comment?
Yeah, I have a question now. Okay, so you know that so the depth search algorithm can be used to compute the extinction time in the SIS model, right? So the extinction time in the SIS model is actually is basically equal to the diameter of the of the region. So do you have an interpretation of this this graph here in terms of some sort of epidemic model? I mean, there is an analogous thing, and maybe I don't know.
Yeah, it's good, very good question. The short answer would be no, I don't know. I think there's some work done in terms of epidemic models. At least I think SIR was considered in some work for random intersection graph. And yes, they use a graph exploration, say like that. But yeah, but I don't know anything beyond that.
Okay. And another question. So you mentioned that at the end of the day, it's your limiting graph is okay. So you were saying something about the random encoding derivative. So I was wondering if your limiting graph is the law of the limiting graph turns out to be absolutely continuous with respect to the limit of the of course before putting the cycles, because of course if you put the cycles
yeah. Oh, you mean in which way? You mean the moderate? So in this thing.
I mean, okay, yeah.
And yes, there's a connection with the Aldous running because of the Brownian scaling. So yeah, so if you want to extract the graph, you only need to consider basically this component, and then you have a scaling property of the Brownian motion, so you can kind of to make it like very similar to these things like here, but you change the parameter lambda.
Okay.
But it's not, so for that it looks like just a multiple, but and then you put into the surplus edges that makes things a little bit complicated. So I think there is an absolute continuity property, but it's not quite quite neat. It's very very involved. The density is very involved.
Okay, thank you.
Is there any other question? So what would be this role of lambda?
So yeah, that's another very good question. So yeah,
I got this question in the social network here.
Right. So it's like, so first of all, we need to again go back to Aldous-Rani. So in Aldous-Rani, you have this similar critical Runde parameter, so this lambda, and then so you increase lambda basically means you increase the edge probability. So your component, so you have more edges, and then your component will merge. So you know in the Aldous-Rani graph that gives you the multiplicative coalescence. So it is actually, there is a similar story for the random intersection graph. You get another coalescence, you get a coalescence process as lambda increase. It's
Okay, thank you very much. Is there any other question? Okay, so let's thank Minmin for this great talk. And see you soon, Minmin, and the other people next Wednesday.
Okay, see you soon. Bye.
Bye-bye. Thank you.